The next stop on our virtual field trip is earthquakes and more volcanoes. Specifically, the earthquake that happened in 1983 around Mount Bora, and relate it to the earthquake that we had at the beginning of the term. This roadside sign on the highway between Arco and Challis explains what happened in 1983, and we will look at some of that evidence. Basically what happened was the tectonic plates in the area were stretched, and as the stretching continued, it created a rubber band effect, and when the rubber band broke, there was an earthquake. One end of the rubber band went upwards towards Mount Bora, raising it 6 to 9 inches. The other end of the rubber band, representing the valley floor, dropped 9 to 12 feet. A nearly 13 feet difference in elevation between the top of Mount Bora and the valley floor. The earthquake that we had at the beginning of the term was similar. The tectonic plates stretched and the rubber band broke, causing the earthquake that we had. I want you to study this picture and see if you can see what is referred to as the scar or scarp line. This is the line that shows where the rubber band broke. In this picture, I have highlighted where that scarp line is. Now, grown in with vegetation, but in the distance, you can see two white scars along the hillside. An upper and a lower scarp line occurred. This scarp line went for nearly 22 miles. The Forest Service has a nice little viewing area and a display that has you standing on the edge of the scarp line. This is very evident where the valley floor dropped and the mountain was raised. A short distance from the Mount Bora display is the town of Challis, and 10 miles to the west of Challis is an area covered with rich volcanic ash. As you turn off the highway and head up Malm Gulch, you will see many interesting geologic features. The first thing that you notice is these Badlands type mountains. These Badland mountains are volcanic ash that was deposited millions of years ago. When you reach the trailhead and walk a short distance up the trail, you will notice outcroppings of limestone beds. This folded limestone is the result of what is known as severe orogeny, which is original mountain building caused by the east-west compression across much of western North America between 140 and 70 million years ago. I have placed my book at the edge of this folded limestone to show you the scale. Continuing up the trail, you will see a different type of sedimentary rock called conglomerate. If you look at conglomerate, it looks like giant cement, which in reality it is. Conglomerate consists of cemented gravel, often with large rounded cobbles. The shape of the gravel and cobble suggest moving water was the main mechanism of transport. The conglomerate bed lies at the base of the Challis volcanics and represents the landscape that existed prior to the eruptions. A little further up the trail, you will notice where ancient and existing stream beds continue to wash the volcanic ash, exposing the conglomerate. At last, you reach this sign that explains how volcanic ash covered an ancient sequoia forest. Sequoia trees grow in a much more humid climate than is found in Idaho, suggesting that the area here had a much different climate. As the giant trees were buried under the ash, they petrified. Because of time constraints and darkness, I was not able to actually get to the petrified sequoia tree. This 1975 photo of geologists standing next to one of the massive sequoia stumps would have been at the end of the trail. One of the sequoias on this hillside measures 9 feet in diameter, and counting the rings yield an age of 500 years old.